All right, next up we have question number 2, fall 15. Back to the normal distribution. So clearly, this is a distribution you want to be very comfortable with. So we have a random sample from the normal distribution with unknown mean mu and unknown variance sigma squared. And we have this quantity s squared, right? Now, the fact that we have a normal distribution is very important because that means we can utilize Student's theorem, right? So we know from students that n minus 1 s squared over sigma squared has a chi-square distribution with n minus 1 degrees of freedom. So I'm proving it's consistent when you show that it's asymptotically unbiased and variance goes to 0. Well, expected value of s squared is going to be based on the fact that the quantity inside this expected value is chi-squared. Since it's chi-squared, this expected value is n minus 1. Because the expected value is the degrees of freedom, right? So that's unbiased. Secondly, we need to find the variance of s squared and show that that goes to 0. It's going to be the variance of n sigma squared over n minus 1 times n minus 1 over sigma squared s squared, right? Now, for variance, we can't just pull it out like we did for expectation. It's not linear like that. Instead, what we need to do is we need to pull it out with the square. So there's sigma to the 4th, n minus 1 squared, variance of a random variable that has a chi-square distribution with n minus 1 degrees of freedom. What is the variance of a chi-squared? Yeah, it's 2 times the degrees of freedom. This would be 2 sigma to the 4th over n minus 1. Clearly, as n goes to infinity, v of s squared goes to 0, combined with the unbiasedness, s squared, conversion probability to sigma squared is a consistent estimator of sigma squared. Part B, how would you construct the 95% confidence interval for sigma squared? Clearly, we want to use a pivot method. We already established in part A that it's a good statistic. So s squared is good. Number 2, n minus 1 s squared over sigma squared is chi-squared n minus 1 is a pivot. It's a pivot because it is a statistic that depends on sigma squared itself, but whose distribution doesn't depend on sigma squared. So it is a pivot. Okay, step 3, we want to go ahead and create a true probability statement with chi-squared quantiles in this case. Okay, so visually we're thinking of this. This chi-squared n minus 1 degrees of freedom. Over here is chi-squared 0.025. Over here is chi-squared 0.975. And the area in here is 0.025, 0.025. That'll give us 95% in the middle. So we got 0.025, 0.975, like that. And then final step in the pivot method is you want to solve for sigma squared in the middle. Okay, and what that's going to lead to is n minus 1 s squared over chi-squared 0.975 less than sigma squared less than n minus 1 s squared over chi-squared 0.025. So our confidence interval will be our lower on the left and our upper